Hello everybody, welcome back. We're going to get started on part 3C of our fluid mechanics work. Today we'll be deriving an expression relating the flow rate to the location of a spherical ball in a rotometer. So if you've never seen a rotometer before, it consists of a conically shaped tube with a ball, and there's flow going through the tube, usually just air, and the ball floats somewhere inside the tube. And so that's what this question is talking about. To start off this question, we're going to need to label some ways of thinking here. So first off, let's start with, as it relates to force balance, the downward direction is positive. We'll also count the bottom of the rotometer to have a diameter of d. Because we don't, and the diameter of D is going to be the same as the diameter of the ball. The reason being we don't want the ball to fall out of the tube when there's no flow going through. So generally speaking, the bottom of the tube has a minimum diameter there of D, which is the same as that of the ball. We'll call this zone 1, which has a cross-sectional area of A1, has flow Q going through it. Okay, so you can imagine flow of like air going through it, right? And we'll leave it at that for now. We'll count here at the central portion of the ball to have, that'll be zone 2. That will have an area of A2, a flow of Q, right? The same flow is going through the whole thing. And then zone 3 up here past the ball. Okay, and that will have an area of A3 if we need it, and again, a flow of Q. A few things that we'll need to observe and also ignore during this problem is that as air flows around the ball and back, the pressure will obviously change throughout these things, but going from zone 2 to zone 3, we're going to count this as a sudden expansion of a gas around this small area, and therefore there will be no pressure recovery. And that would be the pressure recovery from, we'll call it pressure 2 to pressure 3, okay? Likewise, this will be pressure 1 going into the tube. I did mention this is a conically shaped tube, meaning it has some slope to it. We'll call the slope M, okay? And we'll need that as well. Okay, with that, I think we can get started. So let's go ahead and start by writing a force balance equation for the situation we have. Okay, so if downward is positive, what are the forces we need to balance here? Well, the ball has some mass. It has some effective mass based on the density of the ball and the density of the fluid that it's in. Likely the density of fluid, or the fluid that it's in is going to be air, but just in case we're going to make a generalization and just say it's a fluid for now, okay? So, that being said, we have the density of the ball, which I'll designate by rho sub B, minus the density of the fluid, just rho. If we have the density, and we need to give force, we need to multiply our density by the volume of the spherical ball, which is pi d cubed over 6 times the acceleration due to gravity. Okay, that's a force. So we have that force of gravity acting downwards, and then we also have the force due to a pressure holding it up, right? We know that pressure and force are related through area, okay? So we can say plus, now what is the pressure here? What pressure do we use? Well, it's going to be the difference in pressure between both sides of the ball, right? That's the pressure that's being supplied against the gravitational force. So P3 minus P1. Okay. So we have pressure. We know that pressure, area, and force are related. Pressure equals force over area. So pressure times area equals force. Okay, and then our area here is going to be A1. Okay, and if you think about this, A1 is, since it has the diameter of the ball, it's just pi d squared over 4, right? Cross-sectional area. Okay, so there's our force balance equation. And of course, these forces are equal to 0. They're equal and opposite of each other. Okay, so what's our next steps from here? Well, we need to talk about these pressures. Okay, and I mentioned that there's no pressure recovery from pressure 2 to pressure 3. Therefore, pressure 2 equals pressure 3. So that's our first assumption that we need to make. Using this information, we can then use the modified Bernoulli's equation to approach this situation. So you remember from our Bernoulli's equation, the change in pressure, meaning P3 minus P1 over rho, plus the change in the square of the velocities over 2, so V2 squared minus V1 squared over 2 is equal to 0. We are ignoring any viscous effects here. That's just another assumption we're making. No viscous effects of fluid, right? Okay. And you'll notice that I'm using V2 and V1 in 1 and 3 because we said that P2 is to P3. Okay. So we have this expression now. And you'll notice that we have P3 minus P1 here, and we have P3 minus P1 here. So what we can do with this is isolate P3 minus P1. We get rho times V1 squared minus V2 squared over 2, right, is equal to P3 minus P1. Okay, so what we can do is we can plug this back into here and simplify our equation. Okay, right away we can already see that these pi's are going to cancel out. D squared is going to take out D squared there, and we will be able to simplify the 6 and the 4. So let's go ahead and do that. So our new equation now is density of the ball minus the density of the fluid times D over, we'll simplify the 6 to a 3G plus, and we have this expression now is going to be rho times V1 squared minus V2 squared over 2 times 1/2. That's just the simplification of the 6 and 4 there, is equal to 0. Okay, so let's put a pause on this. We have an expression here that we're going to keep, and we'll use that in just a minute. But we need to talk about what velocity 1 and velocity 2 are. We know that the same flow is going through the entire system, but the velocity changes from area or zone 1 to zone 2 as they pass through different areas. We know that flow, velocity, and area are related by the following. Q is equal to V times A, right? So if we write an expression for both zone 1 and zone 2, we get Q equals V1 times A1, which also equals V2 times A2. Okay? With this information, we can set them equal to each other. And derive an expression for the relationship between velocities. We can say that V2 is equal to V1 times the ratio of A1 to A2. All right? Okay, so now let's go ahead and take this equation again and isolate V1 squared minus V2 squared onto one side of the equation. What we'll obtain is the following. So we have, let's see, what's the best way to do this? So I'll subtract this to the other side and then divide out everything, basically. This is effectively a 1/4, right? We combine two 2's there, and we'll move it over so that these two flip again. We get v2 squared minus v1 squared, so we've adjusted for the negative, moving it over. We'll then have to divide by row and divide by 1/4 onto the other side. Dividing by row, we get that, and then dividing by 1/4, we get this. Okay, I think that's good there. And then what we can do now is take this and substitute this expression in for v2. So we're left only in terms of v1, or our initial velocity of the air there. So we get v2 squared becomes v1 squared times a1 over a2 squared minus v1 squared equals this side. Yeah. And then we can factor out a v1 squared. Okay. Factor out a v1 squared, and we get a1 over a2 squared minus 1. And that still equals this side. We can divide by this expression onto the other side, and then take the square root, and we'll get an expression for v1. Okay, so we get v1, I'm going to write it up here, v1 is equal to the square root of, again, we have this, and we're going to divide it by this. So our densities, thirds, what's we have? D G over this term here, which is a1 over a2 squared minus 1. Yep. And I think that's it there. Okay. Great, so that's a big expression there. But we can continue to simplify this, and we have yet to relate this to the height of the ball. So that's what our objective is next. So let's go back to our picture here. What is the height of the ball? Well, we can relate the height of the ball to the diameter and the slope. So that'll be our next steps here. Before we do that, I do want to talk about this term here, because there's something interesting about this term. So think about A1 and A2. So you have A1, which is the area down here, compared to A2. Well, A1 and A2 are very different, as you can imagine. A2 is the area here minus the cross-sectional area of the ball. So it's a very thin opening that the air travels around, kind of in a ring, right? So if this is a cross-section right there, and then you have the ball sitting right here, the area that the air can travel through A2 is only about this big as compared to area 1. So this is area 1, this is area 2. So area 1 over area 2 squared is a very large number in comparison to this 1. So what we can do here is actually just ignore this 1. Okay? We're going to assume that's just a 0 there. Don't need to worry about it. Now that we have this picture drawn, we might as well, let's write out what A1 A1 over A2 squared is. A1 over A2 squared. So we just said A1 is the cross-sectional area of the ball. Right. So it's just pi d squared over 4. But then the area of the ring is a little bit more complex. Right? It's the area of the cross-section of the tube here minus the area of the cross-section of the ball. What we'll do here is we'll call the cross-sectional, the diameter here of the tube. We're going to call this little d, like a little cursive d there. Okay, and that's what we'll use to do this. So here, it's going to look like this. It's going to be pi little d squared over 4 minus pi big D squared over 4. And that whole thing is squared. So that is A1 over A2 squared. Okay. Now, what we need to do is we're going to relate this little d, like we were just talking about, to the height of the ball by using the slope. Okay, it's a linear slope, it's just a cone, right? So what is little d? Well, it's going to equal, it's y equals mx plus b here, right? So you have the original diameter, that's like your b term, plus the slope of the tube times change in height. So there's your, a little out of order, but y equals mx plus b, right? Mx plus b, there you go. So that's how we can relate our slope and our height and our diameter at that point. Okay, so we have d squared in that expression. So d squared is going to be this quantity squared, right? Which is just d squared plus 2mh plus m squared h squared, right? Yeah. Okay, so let's take this and plug this over here. Plug in this over here. We get a1 over a2 squared is equal to, we still have pi d squared over 4 on top. On the bottom, what this really boils down to is pi over 4 times the difference in the diameter squared, right? So we said d squared is this expression here. D squared plus 2mh. Oh, I forgot a d here. 2mhd plus m squared h. Okay, so 2mhd plus m squared h squared, and then minus d squared. Okay. And squared. Okay, so you can see right away that these cancel out, d squared minus d squared. And we're left with 2mhd plus m squared h squared over 4. And then obviously our pi over 4's cancel out here. And we're left with this. Now again, we have another approximation that we can make. M is the slope of this tube. It's very small. I mean, these tubes in real life are hardly conically shaped, but they're really slightly sloped. And then the height of the ball is also going to be very small. It's on the origin of centimeters, or 10 to the negative 2 meters, right? And so when we multiply the squares of these numbers together, it's an extremely, extremely, extremely small number, which we can basically just negate as 0. Okay, we don't even have to worry about this. So what we end up being left with for this a1 over a2 ratio squared is d squared over 2mhd squared. Okay, we can cancel out the d on the bottom with the d squared on top, and we're left with finally d over 2mh squared for this ratio. Okay, and now you can see we've got our height term in there. That's the goal of this whole thing, right? We want to relate all of this to the height of the ball. Okay, so let's go ahead and plug this back in to our expression for V1, okay? And we'll get the following. V1 is equal to, we have the square root of our effective density over fluid density times 4dg over 3, and then our expression here, d over 2mh squared, and the whole thing's under the square root. Okay, we can simplify this a little bit better. We can say square root of our effective density. We will, we're going to flip this, put it up top, 2 squared times 4 is 16. I'm doing too much at once. Let's just do this in a few steps. So we got 4/3 times dg times 2mh/d squared. Okay. And then this we can simplify one more time. And let's make it a little bit more explicit that we're relating this to height. So we'll take the height squared out of the equation and we'll get v1 equals h times the square root of, okay, now we have still have our densities, times, now we're left with 16/3. We have d squared on the bottom and d up here, so we can cancel that, and one of our d's out there. We have one d left on the bottom. We have an m squared up top, and a g. Okay, and I think that's it. We don't need to simplify that anymore. Okay, and so we've done it here. We have our initial velocity of the fluid at a flow rate q going through our rotometer related to the height of the ball through here, with only our other known variables, which is the acceleration due to gravity, the diameter of the ball, the slope of the tube, and then the densities of the ball and the fluid that it's traveling through. And that's all we need to know. So I think that's it for today's video. Thank you guys so much for joining me, and we'll see you on the next one.